Okay, so this is kind of a triumphant moment. We're going to talk about the fundamental theorem of algebra. So the fundamental theorem of algebra states that every polynomial p of x equals a sub n x to the power n plus a sub n minus 1 times x to the power n minus 1 plus so on and so on all the way down to a1x and a0 has n complex roots. So what this means, right, if we kind of set it in layman's terms, so a polynomial of degree n has n roots or zeros, right, depending on which of those words you prefer. So if it's a degree 5 polynomial, it has 5 roots. If it's a degree 49 polynomial, it has 49 roots. What's the catch? There really isn't one. The word to pay attention to here is complex. So there is the possibility that all of the roots are going to be real, like we had in last week's examples. All of the roots we had were real. But there's also the possibility that some of the roots are purely real and some roots are complex, meaning that they have a real part and an imaginary part. So some of the roots may not be purely real, but there will always be n roots, where n is the degree. And you'll notice I also put a little red asterisk here and said up to multiplicity. So this is because roots can repeat, right? So you can have a repeated root, and that's totally fine. So if, for example, I have a degree 5 polynomial, the roots could be 1, 5 repeated twice, 3, and 7. And those two 5s, even though they're not distinct, they count as 2 roots. So there is no guarantee that all of the roots are distinct. There is no guarantee that all of the roots are real. But there is a guarantee that if it's a polynomial of degree n, there will be n roots. So I want to do 2 examples with you in this lesson. And for the first one, we're going to look at finding all of the zeros of this polynomial. We already know how to find zeros of polynomials, so we're going to stick to exactly the same process. So the first thing we're going to do is we're going to find a rational root. And I hope what you remember from last week is, once you find a rational root, which in our case there will always be a rational root, even though there doesn't always have to be one in theory, don't keep looking for rational roots. Once you find one, stop, because there may not be more than one. And if you spend a bunch of time looking through all of the possible rational roots after you've already found one, it might very well end up being a waste of your time. So we'll leave a little space for where we do that. 2, I guess I'll say here, divide out the factor. And I'm going to say here, repeat until left with quadratic. The reason I'm saying this is that in this example, we have a degree 3 polynomial. I did that entirely in the interest of time. But in your homework, you might see an example of a polynomial that's degree 4. Right? And so then after you find the first root, you'll end up with a degree 3 polynomial, so you sort of have to go back to the drawing board. For our purposes, degree 4 polynomials are quite rare, but I just want you to kind of have this cyclical idea in your head that we keep looking for roots until we've chipped it down to where we have a quadratic. Okay, so possible rational roots. I'm going to write here plus or minus p over q. So remember, p are the factors of the constant, which are just 1 and 2. That's nice. The constant is prime. and q are the factors of the leading coefficient. That's also nice because the leading coefficient is 1. So you can see I took a second to pick this example so that it would just be real clean, real easy. So the only 4 possible rational roots are plus or minus 2 and plus or minus 1. In the interest of time, I'm going to go ahead and start in immediately with one that I know will work. But you might first try -1 or 1, and you'd find that they aren't actually zeros. You could do this using synthetic division. I'm going to hop in with 2 to see if that works, okay? So remember, I'm using synthetic division in conjunction with sort of the factor and remainder theorems. So I have here 1, -3, +3, and -2, okay? Right, and I'm testing to see if 2 is a 0, aka if x minus 2 is a factor. So I'm going to drop down the 1. And then it's multiply, add, okay? So let's see what happens. So 1 times 2 is 2. -3 times, -3 plus 2 is -1. -1 times 2 is -2. 3 plus -2 is +1. 1 times 2 is 2. And sure enough, those add to 0, which tells us that 2 is a root of our polynomial. In other words, x minus 2 is a factor. So I'm actually going to go ahead and write here at the bottom that my polynomial p of x that I started with is x minus 2 times x squared minus x plus 1. So you see how here I said divide out the factor, repeat until left with quadratic. Well, I'm already left with a quadratic, so I don't have to divide out any further. But if this had been a degree 4 polynomial, I would have had to do one more round. Now, x squared minus x plus 1 doesn't factor, but not only does it not factor, when we use the quadratic formula, we'll actually see that it has 2 non-real roots. Okay, so we're going to use the quadratic formula here. Use quadratic formula. And this will give us another opportunity to kind of get comfortable with the imaginary number idea. So in this quadratic expression, our leading coefficient A is 1, our middle coefficient B is -1, and C is 1. So this might be a good moment for you to pause the video and kind of set up the quadratic formula and see how you do. Okay, let's go ahead and begin. So -b would be +1 plus or minus the square root of b squared, which is 1, minus 4 times A times C all over 2A, which is 2. So look, here you have 1 minus 4 times 1 times 1, which is just 1 minus 4, and that's -3. So we have 1 plus or minus square root of -3 all over 2. Okay, so this is where we can say, well, look, the square root of -3, we can kind of split that up into the square root of -1 times the square root of 3. And you will remember me saying that I is sometimes defined as the square root of -1. And so what we have here is 1 plus or minus I square root of 3 over 2. So I want to finish this example by actually writing out the roots, because this is going to be something that will carry into the next and final example of this video. So we found that 2 is a root. We did that by synthetic division. And then we have 2 of these other ones. We have 1 plus I square root of 3 over 2. And we have 1 minus I square root of 3 over 2. So what I want you to notice here, and this is a huge deal, is that our 2 non-real roots are actually complex conjugates. This is not an accident. In fact, what you'll see is that any time that your polynomial has a non-real root, its complex conjugate is also a root of your polynomial. So this brings us to our next example. And this is going to be the last example of this video, and you'll have a couple of homework problems like this. So find the polynomial of degree 3 that has a root of 0, has a root of, oops, I missed a 0, 1 plus I, and has leading coefficient 5. So you might be sitting here saying, wait a minute, oops, I missed a piece here. I think I said it, but I didn't write it. Find the polynomial of degree 3 that has these characteristics. So you might be sitting here thinking, wait a minute, you said that if it's degree 3, it's going to have 3 roots, but how come you've only told me about 2 of the roots? Well, I didn't really though, right? I told you that it has a root of 0, and it has a root of 1 plus I, but just a second ago, we also said that if there's a complex root that's not purely real, its complex conjugate is also a root. So if 1 plus I is a root, 1 minus I is a root too. So this is really important to understand, that every single non-real root is going to come in those couples, complex conjugate pairs. Okay, well, let's actually work this out, right? So this is sort of where the factor theorem comes in. It's kind of a morphed factor theorem. If C is a root, then X minus C is a factor. So if 0 is a root, then X minus 0 is a factor. That's just X. If 1 plus I is a root, then X minus 1 plus I is a factor. And if 1 minus I is a root, then X minus 1 minus I is a factor. So here's the beginnings of our polynomial, and we'll multiply this out because I want to make sure that you see it. Let's first kind of clean this up. So we have X minus 1 minus I, X minus 1 plus I. So we're going to multiply this through. We'll get a polynomial of degree 3. What you'll notice, and I'm not going to do anything about this quite yet, but you might be thinking, wait a minute, she said it has to have leading coefficient 5. And I think if I multiply these 3 things together, I'm just going to have leading coefficient 1. What's that all about? And you all actually were thinking about this in last week's homework assignments. That came up there. But we're not going to worry about it quite yet. We're multiplying together 3 things. Multiplication is associative, so you can multiply any 2 of them at a time. So the first thing I'm going to do is I'm going to distribute the X into X minus 1 minus I. And now I'm going to distribute through. So don't forget the distributive property doesn't sleep. We're going to distribute through everybody by everybody, right? So we'll be real methodical about it like so. So we'll end up having x cubed minus x squared plus x squared I minus x squared plus x minus xi. You know what? I'm going to actually move this down so I have a little bit more space. So let's start over here. So we have x cubed minus x squared plus x squared I minus x squared plus x minus xi minus x squared I plus xi minus xi squared. So let's see what we got here. I'm going to highlight with matching colors couples of important like terms. So I have plus x squared I and minus x squared I. So those guys are going to get canceled out. And then I have minus xi and plus xi. So that's really important because those terms with sort of imaginary coefficients are getting canceled. What do I have left? So I have minus x squared minus x squared. So those will combine to minus 2x squared. And then I have minus xi squared. So I hope you all remember that'll end up being plus x. And then another plus x here, so that'll be plus 2x. So I end up with x cubed minus 2x squared plus 2x. So this is a degree 3 polynomial that meets my first two criteria. So it has all of the right roots. It has 0 and 1 plus I as a root. But what about this business of having a leading coefficient of 5? Well, what do you think? So sort of pause the video here for a second and tell me, our polynomial currently has a leading coefficient of 1. How do I make it have a leading coefficient of 5? You're right, just multiply it through by 5. So to satisfy all of our criteria, to have a leading coefficient of 5, a root of 0, and a root of 1 plus I, the polynomial we are looking for is 5x cubed minus 10x squared plus 10x. So what this example really gets at is this idea that every single non-real root is going to be part of a pair of roots that are conjugate to one another. So this is our last lesson on polynomial functions. In our next lesson, we'll move on to talking about a different type of function called rational functions.